Good morning बच्चों myself Purnima. This is my period 4 chapter number 2 structure of atom, and in last period we had discussed about de Broglie's equation, dual behavior of matter, Heisenberg principle, Bohr model for hydrogen atom, and failure of Bohr model. In this period I am taking the topic quantum mechanics, quantum mechanical model of atom, Schrodinger equation, and quantum numbers. Be safe, be healthy, stay at home, and one more thing, be serious with your studies. Utilize your maximum time in your study and learn the things and do the assignments. So I am starting the chapter now. Student, in last period we have already discussed classical mechanics. It is based on Newton's law of motion, and it successfully described the motion of macroscopic particles. But we cannot apply on the microscopic particles, and it fails in case of microscopic particles. Classical mechanics, now what is the reason? Because it ignores the concept of dual behavior of matter, especially for subatomic particles, and the Heisenberg uncertainty principle. Now what is quantum mechanics? It is a theoretical science that deals with the study of the motion of the microscopic objects that have both wave-like and particle-like properties. Actually, Schrodinger modified the de Broglie's equation. De Broglie explained that matter like radiation should also exhibit dual behavior, both particle and wave-like properties, and he gave lambda is equal to h over p, where a lambda is what? Wavelength, and h is Planck's constant, and p is momentum. So he modified de Broglie's equation, and quantum mechanics developed by Heisenberg and Schrodinger. And you know what is Heisenberg principle? Uncertainty. It states that it is impossible to determine simultaneously the exact position and exact momentum. As de Broglie equation was very good, but it is quite complex, and knowledge of higher mathematics is needed to solve it, because when we applied it to find out the speed of the matter, wave is calculation is not measured. Quantum mechanical model replaced the Bohr model of the atom, and according to Bohr model, electrons as particles in circular orbits of fixed radius, whereas quantum mechanical model depicts that electrons as waves spread through a region of space, delocalized we can say, called an orbital. The energy of the orbital is quantized like the Bohr model. Quantum mechanics is based on a fundamental equation which is given by Schrodinger. It is called Schrodinger equation. If we talk about a system, for a system such as an atom or a molecule whose energy does not change with time, the Schrodinger equation is written as H psi is equal to E psi. Now this psi is a Greek letter. It is a Greek letter. It is a complex function. We can say it is not a real number. It is a function of I. It is an imaginary number. H is the Hamiltonian operator, and Hamiltonian operator is an operator which gives the total energy of a system by adding together kinetic energy and potential energy. E is the total energy of the system, and psi represents the wave function. Wave function. Now students, this is Schrodinger wave equation, in which you can see d2 psi upon dx square plus d2 psi upon dy square plus d3 psi upon dz square plus 8 pi square m upon h square bracket e minus v multiply by psi is equal to 0, where psi is the wave function, which is a Greek letter we already discussed, and E is for energy, V for potential difference, H is Planck's constant, and X, Y, Z means this is the three variables. These three variables represents the position of electron, and psi square is we all know that it represents the probability, or we can say the chance to find the electron. So when this Schrodinger equation is solved for hydrogen atom, the solution gives the possible energy levels the electron can occupy and the corresponding wave function of the electron associated with each energy level. Probability density psi gives us the amplitude of wave, or we can say wave function. The value of psi has no physical significance. We can say it is not a real number, it is an imaginary number. Psi square gives us the reason in which the probability of finding an electron is maximum, and it is called probability density. Orbitals, the region of space around the nucleus where the probability of finding, or we can say the chance of finding electron is maximum, is called an electron. Now the wave function may have positive or negative signs in different regions, but if we talk about psi square of the wave function is always positive and gives probability of finding an electron at any particular point. Each solution of the wave function defines an orbital. Each solution labeled by a letter and number combination 1s, 2s, 2p, 3s, 3p, 3d. An orbital in quantum mechanical terms is actually a region of space rather than a particular point. Again I am repeating, actually a region of space, not a particular point. Now what is quantum numbers? Very important topic, and you have to learn them you have to practice them. There are a set of 4 quantum numbers is specified the energy, size, shape and orientation of an orbital. To specify an orbital, only 3 quantum numbers are required, while to specify an electron for all 4 quantum numbers are required. If we have to specify an orbital, 3 quantum numbers are required, while to specify an electron, again I am repeating, while to specify an electron, all 4 numbers are required. Quantum numbers. Solution to the functions used to solve the wave equation. Quantum numbers used to name atomic orbitals. Vibrating string fixed at both ends can be used to illustrate a function of the wave equation. When solving the Schrodinger equation, 3 quantum numbers are used. Principal quantum number n means shell number, which is 1, 2, 3, 4, 5. Secondary quantum number, which represented by L, small l. Magnetic quantum number represented by small m. Now first is the principal quantum number n, defines the shell in which a particular orbital is found, which is represented by n. The principal quantum number determines the size and to large extent the energy of the orbital. The principal quantum number also identifies the shell. With the increase in the value of n, the number of allowed orbital increases. If we can say n is equal to 1, it is the first shell, n is equal to 2, it is the second shell, and each shell has different energies. So if we find out with the help of n the number of orbitals, if it is 1, then number of orbitals 1, if it is 2, then number of orbitals 4, if it is 3, that's 9, and 4, 16, n square, through the formula of n square. And we can also find out the number of electrons. If it is n is equal to 1, then 2 electrons, maximum 2 electrons. If it is 2, then maximum 8 electrons, 3 maximum 18 electrons, and 4 maximum 32 electrons. Size of an electron increases with the increase of principal quantum number n, or we can say, in other words, the electron will be located away from the nucleus. Since energy is required in shifting away the negatively charged electron from the positively charged nucleus, the energy of the orbital will increase with the increase of n. Second is azimuthal quantum number, which is represented by small l. It is also known as orbital angular momentum or subsidiary quantum number. It defines the three-dimensional shape of the orbital. L has integral values from 0 to n-1. It specifies subshell, and each shell contains as many L values as its value of n. So if each shell consists of one or more subshells, the number of subshells in a principal shell is equal to the value of n. For example, in the first shell n is equal to 1, there is only one subshell which corresponds L is equal to 0. If there are two subshells, L is equal to 0, 1. Later designation for secondary quantum numbers: value of L, if it is 0, then S, 1, then it is P, 2 for D, and 3 is for F. This is the subshell notation. If it is the value of n is 1, then L is equal to 0, and subshell notation is 1s. If it is 2, then L is equal to 0, 1, and subshell notation 2s, 2t. If it is 3, then 0, 1, 2, 3s, 3p, 3d, and it is 4, 1, 0, 1, 2, 3, 4s, 4p, 4d, and 4f. The energies of orbitals are specified completely using only the n, l, l quantum numbers. But in magnetic field, some emission lines is split into 3, 5, or 7 components. This splitting describes by third quantum number. The third quantum number is the magnetic quantum number, which gives the information about the spatial orientation of the orbital with respect to standard set of coordinate axes. And ml is an integral volume. It may be either positive or negative. ml's absolute value must be less than or equal to L. If, for example, L is equal to 1, then ml is equal to minus 1, 0, or plus 1. For any subshell defined by L value, 2L plus 1 values ml are possible. For each value of L, ml is equal to minus L, minus L minus 1, minus L minus 2, 0, 1, L minus 2, L minus 1. So this is the chart of number of orbitals. If a value of L is equal to 0, subshell notation 1, and it contains one orbital. If it is 1, then P, subshell notation, it contains 3 orbitals. 2, then D, 5 orbitals. F, 7 orbitals. G, 9 orbitals. H, 11 orbitals, and so on. So each orbital in an atom, therefore, is defined by a set of values n, l, and ml. An orbital described by the quantum numbers n is equal to 2, l is equal to 1, and equal to 0 is an orbital in the p subshell of the second shell. So by this chart we can explain it. So electron spin, which is represented by S, ms. The 3 quantum numbers labeling an atomic orbital can be equally used to well define its energy, shape, and its orientation. But all these quantum numbers are not enough to explain the line spectra observed in the case of multi-electron atoms. That is, some of the lines actually occur in doublets. Doublets means two lines closely spaced, or triplets, three lines closely spaced. This suggested the presence of a few more energy levels that predicted by the three quantum numbers. In 1925, George and Samuel Gordon Smith proposed the presence of fourth quantum number known as electron spin quantum number, ms. An electron spins around its own axis, much in a similar way the Earth spins around its own axis while revolving around the Sun. In other words, an electron has, besides charge and mass, intrinsically spin angular quantum number. Spin angular momentum of the electron, a vector quantity, can have two orientations relative to the chosen axis. These two orientations are distinguished by the spin quantum numbers ms, which taken as the value of plus 1 by 2 or minus 1 by 2. These are called two spin states of the electron and normally represented by two arrows, down, upward spin up and downward spin down. So two electrons have two different ms values. One is positive 1 by 2 and the other is minus 1 by 2, are said to have opposite spins. So an orbital cannot hold more than two electrons, and these two electrons should have opposite spins. So the summary is that M defines the shell, determines the size of the orbital and also to a large extent of the energy of the orbital. There are n subshells in the nth shell. L identifies the subshell and determines the shape of the orbital. There are 2l plus 1 orbitals of each type in a subshell, and that is 1 s orbital, L is equal to 0, 3 p orbitals, L is equal to 1, and 5 d orbitals, L is equal to 2 per subshell. To some extent, L also determines the energy of the orbital in a multi-electron atom. ML designates the orientation of the electron of the orbital. For a given value of L, or has 2L plus 1 values, the same as the number of orbitals per subshell. It means that the number of orbital is equal to the number of ways in which they are oriented, and ms refers to the orientation of the spin of the electron. So students, you just learn them, revise them, and I will give you the assignment for this by giving some examples. Thank you.